In this video, we're going to go through 3 different calculations of an ideal gas. So we're going to have a look at the normal molar gas or ideal gas formula, that is. We're going to have a look at using the graph to find the change in temperature, and we're also going to have a look at using one of Boyle's law, Charles's law, or pressure law. So it tells you that figure 1 shows how the pressure varies with volume. There's an area where pressure is sort of inversely proportional to the volume, and there's an area where pressure is constant even though there's an increase in volume. Do bear in mind that pressure is given in 10 to the power of 5 and volume is given in 10 to the power of minus 3, in case you can't quite see that. It also gives you the temperature, but that's in degrees, and I'd always recommend you convert into Kelvin before you do it in calculations. It says calculate the number of gas molecules trapped at position A. Well, what do we know at position A? We know the volume, we know the temperature, which we can convert into Kelvin, we know the pressure, and do we know anything else? We do not know anything else. But what we can use to find the number of gas molecules is the equation that pressure times volume is equal to the number of gas molecules multiplied by Boltzmann's constant multiplied by temperature. Making capital N the subject of the formula, we'll be able to find the number of molecules. So that's pressure times volume divided by Boltzmann's constant multiplied by temperature. Now pressure at A is 1 times 10 to the power of 5, so let's write that out. The volume at A is, just read off the x-axis, is 0.7 times 10 to the power of minus 3. We then divide all of that by the Boltzmann's constant, which is 1.38 times 10 to the power of minus 23, and multiply onto that the temperature, but in Kelvin. So 27 degrees, you add to 273 to turn it into Kelvin. In case you guys do forget that, just do remember that 0 Kelvin is absolute 0, which is correlated to minus 273 degrees. And you'll know that the Kelvin is always 273 more than the number of degrees. 27 plus 273 will give you 300. I'm just going to very quickly type that into my calculator. I have done this question before, so I feel like it's 1.38 times 10 to the 22. But yeah, I don't expect myself to remember that. I'm just going to very quickly do this. 1.38 times 10 to the power of minus 23, all multiplied by 300. And it's 1.69 times 10 to the 22. Yeah, so I remembered it wrong. It's good that I checked. Perfect. Let's now move on to the next part of the question, which says calculate in Kelvin the change in temperature in the compression between A and B. So what's different between A and B? Because it's still at that same temperature. Sorry, not at that same temperature, it's at that same pressure. Well, the volume is what's different. What we can do is find the temperature of B, at point B, because we now know the number of gas molecules, and of course that's not changing. If we rearrange this equation, this time for the temperature, we can get that the temperature at B, I'm just going to write a subscript of B for representative of the temperature at B, is equal to the pressure at B multiplied by the volume at B, all divided by the number of gas molecules, which is the same at B and A, so you don't need to put a subscript of B, multiplied by gas constant, the Boltzmann's constant, which is also the same. Now, in this case, the pressure at B is 1 times 10 to the power of 5 again. The volume at B is what's different, and that's 0.5 multiplied by 10 to the minus 3. All divided by the number of gas molecules, which is the same as the number that we found just previously, 1.69 times 10 to the power of 22. And multiply into that the Boltzmann's constant, which is 1.38 times 10 to the power of minus 23. This number that I know, by the way, because I've done these questions quite a few times, it is on your equation sheet, so you don't need to memorize it. I'm just going to very quickly put that into my calculator. So 0.5, and then here we have, feel free to skip ahead a few seconds if you like. 10 to the power of 22, and that's all equal to 217 Kelvin. Now you might think, okay, that's quite a big change between 27 and 217. Well, that's because this is in degrees. We have to also convert that into Kelvin. And once we do, we get that at A, the temperature is 300 Kelvin, whereas at B it's 217 Kelvin. So the change in temperature is a subtraction of the larger one and the smaller one. In this case, 300 take away 217 is 83 Kelvin. And that's your change in temperature. That's everything for that question. So let's now move on to part 4. It says deduce whether the temperature of the gas changes during compression from B to C. So now we'll focus on this section of the graph. Well, let's think about it. If the temperature is constant, because this is an ideal gas, then Boyle's law should be valid. So if we prove that Boyle's law is valid, that proves that temperature is constant. So what is Boyle's law? It tells you that pressure is inversely proportional to volume. If that's the case, then pressure is equal to a constant over volume, or in other words, pressure times volume is constant. That's important because if we show that the pressure times volume at B is equal to the pressure times volume at C, that means that pressure times volume is constant and Boyle's law is applicable, so temperature is constant. So let's do that. Let's first find the pressure times volume at B. So pressure of B times the volume of B is equal to 1 times 10 to the power of 5 multiplied by the volume at B, which is 0.5 times 10 to the minus 3. All of that multiplies to give 1 times 10 to the power of 5 multiplied by 0.5 times 10 to the power of minus 3. That's 50. Let's now check if the pressure at C times the volume at C is also 50. So that's going to be equal to, 2 times, so the pressure there is 2 times 10 to the power of 5. We multiply that by the volume at C, which is 0.3 times 10 to the power of minus 3. And that gives you a value of 60. So we see that pressure times volume is not constant here. That means that Boyle's law is not applicable, so temperature is not constant. And that's it. That's everything for this question. Be sure to leave a like if this video helped and subscribe. I'd appreciate it a lot. If you have any tutoring inquiries, I think my website's linked, first link in the description, so be sure to reach out, and yeah, I look forward to hearing from you.